Hello together. I'm Johannes Vater, external PhD candidate at BMW and supervised by the Technical University of Munich. Today, I would like to present you my paper titled Closing the Loop, Real-Time Error Detection and Correction in Automotive Production using Cloud Architecture and a Convolutional Neural Network. Therefore, I would like to start with the agenda. As you can see, I have divided my presentation into 7 points. I would like to start with the motivation or business understanding. Following this, I will explain you the generation of our dataset and then present the preprocessing of the data to you. Then I will discuss the development of our convolutional neural network, which I will call CNN in the following. And in point 5, I would like to introduce you to the evaluation of the CNN. In order to be able to use the CNN in the production context, an AT architecture is required, which I will present you in the 6th point. This architecture is based on the cloud and edge computing. Finally, I want to validate this architecture too. Let's start with the development of the CNN and the business understanding. As already mentioned in the title of the publication, this paper deals with the manufacturing of the stator of an electric motor. To increase the power density of the electric motor, it is necessary to develop new and innovative technologies for the production and to increase the efficiency of the electric motor. The so-called hairpin technology is a novel technology to increase the efficiency of the motor by replacing traditional copper windings with thick copper bars. As you can see on the picture on the left side, the main process steps of the manufacturing are the deformation of the hairpins, followed by the insertion of the hairpins into the metal package, and afterwards the free ends of the hairpins are twisted and finally connected via laser welding. The problem with this process is that copper has strong reflective properties and can therefore hardly absorb any radiation. For this reason, a higher laser power must be set than for welding steel or aluminum, and as a result, the welding of the hairpins can lead to so-called insufficient welding, welding spatter, and welding crater. Even if an error occurs, the motor is produced completely and must be removed at the end of the line after electrical test. Afterwards, the connection panel has to be disassembled and the welding of the hairpins must be manually reworked. This, of course, takes a lot of time and costs a lot of money. As shown on the picture on the right side, the goal is to detect and eliminate incorrect welds using rework concepts in the line so that the product finally meets the desired quality deviation. Therefore, it is essential to detect and eliminate such quality deviation in an early stage and in real time. Computer vision in combination with machine learning is an important enabler for this. The convolutional neural network, therefore, is a good choice. As I already told you, we have 4 different faults: correct welding, insufficient welding, welding crater, and welding spatter. These 4 error classes were explored with an expert, and in addition, the classes are further subdivided, as you can see here. The amount, the quality, and the class balance of the available data is an important factor for data-driven technologies. Therefore, the procedure of data generation has its goal in generating the largest possible number of data with good quality and under realistic condition. Based on these conditions, a realistic procedure for generating data with high quality was developed, as you can see here on the picture on the right side. As a result of this data generation procedure, it was possible to produce around 550 to 600 labeled glass, black and white images, and 3D scans of hairpin welds for each class with different severities. This data was divided into training data and validation data with a ratio of 80% to 20%. To further increase the number of samples in a training set, we used data augmentation. As a result, one image could be used to create 49 other similar images. Based on this, more than 90,000 training images were generated for the data-driven learning process, and about 450 images were available for validating the model. Using the same CNN without a data augmentation, the accuracy of the validation set is just around 94%. We preprocessed our data to increase the resulting performance of the classifier and its accuracy. In the following, I will present you the preprocessing of the 3D scatter. The images are cropped around the center of gravity with the size of 450 to 450 pixels, as you can see here on the first picture. The color of the 3D scan is converted into height information, as you can see in the second picture. Afterwards, we cut out the hairpin in Z direction, so that only the top of the hairpin is highlighted, as you can see here on the third picture. The 3D data were reduced to the size of 30 to 30 pixels, and in addition the attitude range was scaled into a range between 0 and 255, as you can see here. The preprocessed image was saved as a grayscale image, as you can see here for welding spatter and here for welding crater. Further, normalization is an important task. Here a normalization technique based on the subtraction of the mean of one pixel over the whole dataset by dividing it by the standard deviation of this pixel is used. As you can see here for welding spatter and here for crater, the spatter is highlighted because of the normalization. The preprocessing of the black and white pictures only includes step 1 and 4. The proposed CNN was basically developed by studying the structure of the well-known VGG network. This structure is based on convolution blocks built of multiple convolution layers followed by a pooling stage. The generic structure of the developed CNN architecture, the input data and the output of the neural network are illustrated in this slide. The model proposed in this paper is made up of 4 convolution blocks. The first convolution block consists of 2 convolution layers, each with 8 kernels of a size of 3 to 3 pixels, followed by a batch normalization and a ReLo activation function, as you can see here. After this, a max pooling of a size of 2 to 2 pixels is used. The second, third and fourth convolution block basically have the same structure as the first one, but with a doubled number of kernels after each repetition, as you can see here. We have here 16 kernels, here 32, 64. The fourth and last convolution block is followed by a global average pooling, as you can see here. The fourth convolution block is followed by a dense layer, a fully connected layer, a batch normalization, ReLo activation function, and a dropout layer. Finally, we have a softmax function of 4 neurons, one for each class. On the left side of the picture, you can see the evaluation of the CNN with black and white images as an input. It can be seen that each case an inefficient welding, a welding spatter, and a welding crater was predicted as a correct welding. This is very dangerous for the production because defective components can be delivered to the customer. Furthermore, many correct welds are predicted as welding defects, as you can see here, which increase the rework effort. As can be seen in the table, the accuracy is only 95% and the recall is also less than 94%, as you can see here. On the right side, however, the results with the 3D scans as an input variables are shown. It is clearly visible on the diagonal of the confusion matrix, as you can see here, that the convolution neural network was able to correctly classify almost all test data. Thus, an accuracy of 99.28 and an average of the 5-fold cross validation was achieved. Due to the significantly better test results with 3D scatter, only a 3D scanner is used as a sensor in the following. For a 100% inline inspection by a convolution neural network and automated adjustment of the process parameters, an appropriate IT architecture is needed. Therefore, I will present you in the following our architecture, which is based on edge and cloud computing. To implement this process, we have designed a cloud and edge-based architecture. This architecture is divided into 3 parts: the production environment, the cyber-physical production system, and the cloud. The production level contains all production units. The cyber-physical production system is close to the production line. and it contains all necessary components to classify the defects and to initiate a rework. The actual edge device is also located in it. The edge device is an industrial PC which provides the necessary computing power. Last but not least, we have the cloud. This is a remote computing and storage component. As you can see, the software modules are containers. This has the advantage that the containers can run on different operating systems. These modules use MQTT as a protocol. It can also be seen that we use Microsoft Azure as a provider. I will now describe the individual levels in more detail. In the production environment, the actual production line is located. In the paper presented here, this is the hairpin welding station. In the cyber-physical production system, among other things, the sensors and actuators are localized. As already mentioned, we use a 3D scanner as a sensor, which sends the image to the edge device via FTP protocol. The PLC acts as an actuator. With this, the rework can be controlled. The edge device is divided into two levels, the cyber-physical interface and the processing layer. The cyber-physical interface serves as an interface to the sensors and actuators. Thus, it is an interface between hardware and software. Furthermore, it enables the communication to the cloud. The processing layer is where the actual processing of data streams takes place. In the preprocessing module, the incoming 3D scans are preprocessed in the same way as the procedure presented before. Afterwards, the error case is determined in the prediction module. The convolutional neural network presented before is located in this module. Based on an error case, a rework strategy must be determined. The respective rework was determined with an export and tests. Based on a decision tree, the decision module selects the appropriate rework. In a validation module, it is tested whether the rework currently is possible. Possibilities such as the failure of the production line or compliance with the cycle times are checked. Finally, the variable is sent to the PLC via the cyber-physical interface, so that the error case can be reworked automatically and in real time. As I already explained to you, we also use the cloud. All data is stored in the cloud so that the CNN can be retrained as the environment condition can change. A PostgreSQL database and a blob storage is used for the data storage. Furthermore, the software modules are managed via the cloud. This means that changes of the software modules can be easily made without the need for an employee to adjust the changes directly on the production line. Finally, I would like to show you some results of the IT architecture. For this, we have evaluated various timestamps, which you can see here above. These are the timestamps of the individual modules, as well as their communication with each other. We tested more than 50 stators. The mean of the timestamps you can see on the table above. It is easy to see that the time of 21 seconds was achieved for complete stator. Thus, the cycle time required of 30 seconds could be undercut by a factor of 0.7. It can be also seen that the preprocessing module, as you can see here, has the highest processing time. Thus, this has the highest optimization potential. In conclusion, however, it can be said that the system is optimally suited for the series production. Finally, I want to thank you for your attention, and I'm looking forward for the conference. See ya!